So an incline problem is when you have a box, something like this, that's sitting on a ramp, otherwise known as an incline. It's going to go down the incline like that. And to understand this, we first need to look at a box when it's just sitting on the ground. So something like this. Here you've got a box sitting on the ground. You've got a normal force pointing up like this. You've got a gravity force pointing down like this. So the sum of the forces is 0. Well, how does this differ from a box that's sitting on an incline? Well, an object that's sitting on a slope still has a normal force that is perpendicular to the incline itself, and the gravity force still points directly down. So going back to the original box, just sitting there on the ground, seeing that the gravity force is pointing down, the normal force is pointing up, let's apply an XY axis on this so we can sort of get the orientation. Okay, so now a coordinate axis has been added. You can see that the positive X over here, negative Y is down here, negative X is here, positive Y is there. This helps us to get our bearings. Well, if you take this whole object here and you put it on an incline, what's going to incline is not just the ground itself, but so will the entire XY axis. Let me show you in the next frame. Okay, so now I've tilted the ramp up at some angle theta, and there's the normal force still going up, gravity force still going down, but let's apply the XY grid across it again, all right? So now when I overlay the XY coordinate axis, you can see that the x-axis is still parallel to the ground and the y is still perpendicular to the ground. The normal force remains perpendicular to the ground, but the gravity force still points down to where the original ground was. So it no longer is along the xy axis grid. And in fact, the angle that separates the gravity force from the negative y-axis right here is exactly the same angle that was made when the incline was raised up relative to the horizontal ground. The angle theta that the incline is raised relative to the ground is exactly equal to the angle theta that the force of gravity is separated from that negative y-axis. And here's why that's important. See, you can take that force of gravity and attach it head to tail to the normal force up here like this. And of course, the angle remains the same. So now what we've done is we've added the vectors head to tail. And of course, whenever you add vectors head to tail, you get a resultant vector that starts at the tail of the first vector and ends at the head of the last vector. And that's going to look something like this. Just like that. And that's your resultant vector, or force resultant. Well, this force resultant is the force that's acting down the hill. So it's the box itself moving down the hill. That's the resultant force. So let's identify the parts of that triangle. This part, of course, this is the normal force. This is the force of gravity. So that force resultant, if you take a look, that angle right here being theta, and this being the hypotenuse, that makes force resultant right here, mg times the sine of theta. And that is the force down the ramp. Now let's take a look at this from a different perspective. So another way to look at this is to look at your force of gravity, which is acting this way, and think of its two components. So it's going to have two components, one here, force of gravity, which is going to be parallel to the hill, and force of gravity, which is going to be perpendicular to the hill. Force gravity parallel and force gravity perpendicular are going to form a right angle right there. And again, you should notice that force gravity parallel is indeed mg sine theta. Get the exact same result. In addition, notice that force gravity perpendicular is equal but opposite to the normal force. This is Newton's third law. For every action, there's an equal and opposite reaction. This helps us to define that the force of gravity perpendicular is indeed mg cosine theta, which means that the normal force is also mg cosine theta. And this is going to become important very soon because the normal force helps us to determine the force of friction. So here's a drawing cleaned up, just so you can see that it's mg sine theta, and that's the force that's acting down the ramp. It's the sum of the two forces, the normal force, which is acting in this direction, and the gravity force, which is acting in that direction. That is the net force that's acting in the downward direction. Not only that, but if you take a look at this, since F equals ma, if you get rid of the m, then what you're finding is the acceleration equals acceleration. So if we get rid of this m right here, what we have found is we found the acceleration down the ramp. So you can either look for the force down the ramp or you can look for the acceleration down the ramp. Both are g sine theta. The reason why finding the acceleration down the ramp is important is because once you know that, you can use it to solve a kinematic equation, something like v is equal to v naught plus a times t. That a that's right there, that's the g sine theta. Something else to think about here is force of gravity parallel to the hill which we know is mg sine theta, is equal to, but is opposite the tension that's shown here in this diagram. That means this tension force here is opposite to the mg sine theta, the force that's acting down the ramp. And that's important because you might be asked what tension force could be added here that would keep the block still or move at a constant velocity. Well, it would be mg sine theta. Let's take a look at a sample problem for an incline. Here we have a skier who has a mass of 50 kilograms, and he's on an incline that's inclined 30 degrees relative to the horizontal, and he's going down a complete height of 5 meters. So if we assume that this is a right angle over here, that means that the sine of angle 30 is equal to the opposite over the hypotenuse. And angle 30 is a very common angle used on the subject test, and that's because the sine of 30 is equal to 0.5, 1/2. This means that if the opposite side is 5 meters, then the hypotenuse has to be 10 meters in order for the sine of 30 to be 0.5. So now let's label the length of that ramp 10 meters. And now that we know the length, let's take a look at a couple of things we've already discovered on the previous slides. We know, for example, that the force down the hill, or the force of gravity that's parallel to the hill, is equal to mg sine theta. We know that the mass of the skier is 50 kilograms. And on the subject test, we can always assume that g is equal to 10 meters per second squared. And of course, we already determined that the sine of 30 is equal to 1/2. So that gives us a force down the hill of 250 newtons. And you should recall from before that this g sine theta right here, the 10 times the sine of 30, that is the acceleration down the ramp. So now, not only do we know the force down the ramp, but we also know the acceleration down the ramp. And that acceleration can be used in kinematic formulas like v equals v naught plus at, or x equals v naught t plus 1/2 at squared. The a in that case is going to be 5 meters per second squared. And in the case of x here, well, that's the 10 meters that he's going down the ramp.